Right now, I'd like to introduce Kush Gulati from Omni Design.
Good afternoon, guys. Thanks for being here. Thank you very much for the introduction. My name is Kush Gulati from Omni Design Technologies. I'm going to be talking about advancing the state of the art in high performance, low power data conversion technology. All right, we're going to start by introducing some of the team members in the company, as well as the company products and technology. We're going to look at some analog to digital converter trends. As you guys know, A to D conversion technology has changed quite a bit in the last couple of decades. And what we're going to look at is essentially go back in time and do some historical perspective on how it has changed. Then we'll discuss Omni Design's technology and see how we stack up to the rest of the world. All right, to introduce myself, I have been designing high-performance, low-power analog mixed-signal circuits, good stuff, for the last 2 decades. I have a doctorate from MIT in 2001, and Omni Design happens to be my 5th startup since I graduated. So it's been quite a lot of entrepreneuring, right? 2007, I founded, along with Professor Harry Lee from MIT. He was my advisor at MIT. A company called Cambridge Analog Technologies, an ultra-low power ADC IP company as well, which was acquired by Maxim Integrated in 2011. Okay? Subsequently became the general manager and executive director of their advanced IP solutions group. We were essentially building IP products for the whole company. And in 2015, Professor Harry Lee and a few other guys, including a couple of guys right here, Sid and Hyun, founded Omni Design Technologies. What do we do? Our mission is to develop and license disruptive semiconductor IP core to enable the world's most advanced and sophisticated systems on chips. As you know, chips have been changing a lot. It's getting more and more complex. Chips that used to be on a printed circuit board are now part of the same silicon, right? So in that new world, right, we are positioning Omni to be at the front and center of that evolving trend. We have invented what we believe is the world's lowest power switch capacitor analog processing technology. We are leveraging this technology as well as some other techniques to provide innovative solutions for analog mixed signal IP cores for a variety of applications. We are staffed by some amazing people, both those who have a good amount of industry experience, as well as world-class technologists from schools such as MIT, UIUC, etc. So these are this is the leadership team. Besides myself, we have Haisung Lee. He goes by Harry Lee from MIT. He's a professor. He, again, was my co-founder at CAT and my advisor at MIT, so we know each other a really long time. He's our chief technologist. He happens to be one of the foremost experts in analog to digital converter pretty much since he did his PhD thesis under Paul Gray in 1984 in UC Berkeley. Sid Datta and Dr. Dennis Daly are our vice presidents. They have, again, really strong industry experience, a lot of production chips. But more importantly, they have been leaders in some of the most complex products that I know of. Okay? Pawan Hanumolu is our principal technologist. He's a professor at UIUC and is part of our think tank in developing innovative solutions in the analog mixed signal area. Hyun Bu is our engineering director. He too has a PhD from MIT, and he helped develop some of the initial core concepts in the Swift technology that we will talk about a bit later. All right, together, this collectively, the leadership team has more than 145 years of experience, a lot of patents, more than 100 silicon products, lots of publications in ISSCCs and JSSCCs of the world. And again, most importantly, many of us have been leaders in the some of the kind of key products that have been introduced in the A to D world and other analog signal area. We have a distinguished advisory board, including Professor Anantha Chandra Kasan, who is the head of department of the Electrical Engineering Computer Science Department, as well as Drew Peck, Dr. Dirk Lockeen, and Veng Shukla. We have 2 different centers. We are essentially on both coasts, and the advantage that brings to us is as follows. Boston Design Center is excellent for recruiting from MIT and other kind of industry from that area. And our corporate headquarters being in Silicon Valley is very close to many of our customers, so it helps a lot tremendously. we have 4 basic focus areas. These are not non-overlapping. They have significant amount of overlap. The analog mixed signal focus is essentially one where we develop high resolution, high speed data converters, both A to D converters and D to A converters. The A to D converter stuff we're going to talk about a bit later, as well as things like temperature, voltage monitor, and other things. In the wireless communications and infrastructure space, what we do is we take the A to D converters and E to A converters that we develop in the first area and customize them, right? So both the wireline and the wireless communications area require significant customization. They may need certain special types of equalizers or filtering or gain control and so on and so forth. So we kind of adapt our data converters to those different specific areas. In the wireline signal conditioning, orthogonally to the data converters, we also have redrivered retimer technology that allows us to extend cable length. Okay. We are also developing a connected sensor platform. And what does that mean? It's essentially a collection of really low power analog IP that customers need to build their IoT chips. Okay. We're going to do a deep dive. Sid Datta right here is going to do the deep dive on this platform tomorrow at 4:30 p.m. So please come back and check us out. Okay, so let's now take a step back and look at some historical trends. Okay, we're going to start in 1997. The orange bubbles right here represent, each of these bubbles is actually a performance representation of a unique A to D converter that was built and published in either one of these 2 conferences. Okay, ISSCC, which is the International Solid State Circuits Conference, and the VLSI Symposium. Now, these 2 conferences tend to be pretty much the premier conferences. Therefore, it's fair to assume that every data converter published there, or most data converters published there, are pretty much state of the art and lead the industry. Okay, so these are pretty much best in class in the year that they were published. All right. The x-axis is Nyquist sampling rate, or more precisely, it's a normalized Nyquist sampling rate. This allows for combining data from oversampled data converters as well as those that are Nyquist converters, such as pipeline ADCs, right? The y-axis is figure of merit, which is defined as the following equation: power divided by the 2 times the maximum input frequency that is sampleable by the ADC, times 2 to the power of effective number of bits. Okay. What is the significance of figure of merit? Essentially, if you have lower power ADCs, your figure of merit is going to be lower. If you have higher performance ADCs, either sampling rate or ENOP, your figure of merit is going to be lower. So low form is good. Really the significance of form is that it allows us to compare, at least provide a yardstick to compare ADCs across varying resolution and speed. Okay, it gives us a method to compare wildly different data converters. It's not perfect, but it helps. Okay, so let's go back to this chart. I'm going to play a short video now, and essentially what you'll see is the years incrementing, and these orange bubbles kind of vanish, and new bubbles take their place as the years progress, right? Note that the y-axis is log scale, so small movements here mean a big deal. So as these years increment, you see these orange bubbles moving from the top left towards the bottom right, right? Lowering power consumption and increasing in Nyquist sampling rate, right? For the most part, the trend line looks like this. There are some converters on the left side which are extremely low frequency, high resolution. Those are targeted to some very specific applications. Now, let's see the video one more. Oops. Let's do it again. Okay, let's watch the video one more time. See, the number of points keeps changing. That depends on the number of ADCs being built that year, right? Okay. So let's look at all the data points. It's quite a big spread, massive number of magnitudes, orders of magnitude, right? Difference in figure of merit, right? If you compare 1997 to 2016, this is what you see. Blue dots, 1997, 2016 is red. If you compare the two, you find, generally speaking, it's much more than a 100x improvement in figure of merit, right? And this really corresponds to if you do the math, a 2x reduction in power consumption every 2 years. This is absolutely amazing change in power consumption. How has this happened, right? There are two fundamental reasons. One is process scaling, right, helps reduce power consumption naturally. The other factor is pretty much human ingenuity, which has led to advances in circuit techniques, new circuit techniques, innovation circuit techniques, as well as new architectures. What do I mean by that? So what you see on the right side is a collection of architectures that you have seen in all of these data points. There are almost 50 different architectures represented here. And we know they're not 50 different fundamental architectures, right? So what people have done is taken some very basic fundamental ADC architectures, such as pipeline, SAR converters, flash, and so on and so forth, and made basically created a bewildering array, right, of hybrid architectures. And this is part of the reason you see this massive improvement in figure of merit. Okay? And these colors here are really representative of each of the different architectures. Quite interesting to look inside and figure out which architecture is winning, but that's for a different time. All right, so let's go back to Omni design and our technology. We call this technology SWIFT, switch capacitor fault tolerant technology. I'll explain the name shortly. Is what we believe is a truly disruptive technology, right, that enables a combination of ultra low power, kind of very low power, high performance, as well as design simplicity. Okay, so it improves the power consumption. It allows us to increase the channel speed. So in other words, what was possible at 200 megacell per second, now it's possible for us to go to 400 megacell per second, all things being equal. Okay. It also simplifies the analog block specifications. What does that mean? An op-amp design, for example, can tolerate much lower gain. Okay, so a pipeline design typically requires a 14-bit design, for example, requires tens of thousands of DC gain, right? Whereas using SWIFT technology, you can reduce the gain by almost 10x, depending on the speed and resolution. And this is, again, function of the specifics of the design, what ENOB you're targeting, and so on and so forth, but there is a massive reduction. What does that mean? It means that you are more tolerant to process voltage and temperature variation. So essentially, this technology is more tolerant to PVT variation. So we exploit all of these three attributes in our designs, and that explains why we call it fault tolerance. It's not the fault tolerant in the redundant type of, in the way, but it is tolerant to PVT variation. Okay, so this is a measurement result that I would like to share with you. This is a 250 megasound per second converter. It's publicly available. It's at 250 megahertz sampling rate. The signal to noise and distortion ratio and SFDR are very respectable. When you push the input frequency, the SNDR remains relatively flat, so pretty strong, good performance. When you change the sampling frequency, on the other hand, the SNDR also remains pretty flat until beyond 250 megasound per second, which is its rated maximum frequency, right? Now, how do we compare to the rest of the world? So these are the data points we just saw, right? And to kind of enable a fair comparison, what we're going to do is constrain this data set to those types of resolutions and speeds that are equivalent to what we offer, right? The constraint we use specifically are the following three parameters: SFDR greater than 75 dB. That's a pretty commonly used number by many of our customers. In fact, all three numbers are chosen specifically to be a very practical kind of constraint that stems directly from what we see customers desiring from our products, especially those that come from the communications side of things. ENOB of 10.5, fairly standard, and FS greater than 200 megasound per second, again, a very, very standard request. So if you do that, you get only 4 points remaining on this entire chart. And if you zoom in to this box here, this is what you see. And the lowest data point on this, this called Hyunwoo ISSCC 2015, is actually the genesis of our technology. Okay, it's much significantly lower power than anything else that has ever been presented or published. Right? Now, what we have done at Omni is taken that technology and we licensed it from MIT, and then significantly improved upon it. So SWIFT really is a derivative of that technology that was published. and we've improved upon it by reducing the power consumption still further and increasing the channel speed. Okay, and we're still working on that. We expect to go to 500 and beyond single ADC channel speed. Okay. We're also developing higher speed data converters, such as this 1.2 gigasample per second, which we are going to be delivering to customers. And so if there's interested parties here, please come over to meet us after the talk. And of course, we're also developing things that are beyond these frequencies, 3 gigahertz and beyond. So we did a comparison with the academic side. Let's compare against the industry, right? So we took 4 of the top IDMs developing data converters, 4 top companies in the space. And to make it fair, we stripped those converters of ancillary circuits. In other words, we don't count the power consumption of the digital side and so on and so forth, the I/O and whatnot. If you do a normalized comparison for the same signal-to-noise and distortion ratio, we find that we are significantly lower in terms of power consumption. It's not even a comparison. All right, with that, I would like to conclude. Thanks again very much for your interest. And again, explore Omni Design IP at the ChipEstimate booth. Come to talk to us, and I'm happy to answer questions.
Kush, thank you so much. Any
you.
questions for Kush? Anything at all? No? Okay. But, you know, they all know that they can find your IP.
Can I ask questions? No.
Yeah. Available on ChipEstimate.com.
Actually, I do have one question. How many of you guys design ADCs? Or cool. And how many of you buy ADCs? Okay, not too many people here.
This is the marketing group from
okay.
Synopsys there.
Oh, okay.
Just kidding.
Okay, great. Again, thanks very much.